Yeah, well, hello everyone. I'm very excited to be here to announce what I believe, we believe, to be a breakthrough in far UVC LED performance. And it's vis-a-vis a fixture. As you know, the LEDs need to go into something, a fixture. This is our fixture. It's a 6 millimeter by 40 millimeter aluminum panel. And what we did was we got hold of some LEDs from Selena, and we tested them in our fixture. And what we found was quite, we think, spectacular. So again, this is our fixture. It's a close-up. The wavelength of the LEDs are 235. And what we got was 3 milliwatts power output, 100 milliamps. This per LED. And these were certified by a third party, the Danish Technological University. And we have them in our fixture. We put 3 in. You can see on the far right. There's 1 in each, 3 LEDs and 1 fixture there in an array. And the 3 diodes together gave a 9 milliwatt output. So we were quite excited by this, not so much because of the output, which is actually pretty good in itself, but because we achieved only 37 degrees junction temperature, which for those of you in the LED business know that heat is a major problem and lowers the lifetime of an LED, but also the performance is improved with the lower temperature. So with this exciting data with a low junction temperature, just to give you an idea, normally I believe Selena's maximum junction temperature is 85 Celsius. So we are at 37. And that's at 100 milliamps, which is a pretty good, pretty high current. Okay, this is just to show you how we tested in-house as well, the approach we took. But with those results, we then went and increased the current to see how high could we go and what output could we get while keeping the junction temperature low. And we achieved 6.3 milliwatts at 250 milliamps. And one might say, well, at 250 milliamps, the junction temperature is going to be way too high. But 58 was what we got, which is still well below the 85. Let's say maximum. Here's just to show you, as we increase the current, we get a better optical power up to 6.3 at 250 milliamps. And again, the junction temperature at 100, 150, 250, and maximum junction temperature at 250 was 58. And again, as I just said, 85 is sort of the absolute maximum you can get. So how was this achieved? We believe it has to do with heat dissipation, the ability of the fixture to conduct heat away from the LED. And we're not using active cooling, so that's a key point. We're not pumping anything or circulating air around it. It's just purely passive. So, as I said, this is the fixture we use. It's just basically 2 aluminum plates, very simply put. 2 aluminum plates put together with the LEDs, you can see them. And you can see the aluminum plates here. and you have then the temperature differences we measured. And again, the heat dissipation, we think the key reason for why this junction temperature is low, and the wall plug efficiency of 4 UVC is so low right now that most of the energy applied to the device is converted to heat, which is why when we get the heat out, we're able to get a low junction temperature and push the current to a higher number. This is just to show the inner workings of the fixture. We believe that the reason why the fixture is one reason why the fixture is effective at conducting heat is because it's anodized aluminum, and the anodized aluminum has a very good heat radiation emission coefficient. Here you can see roughly how we calculated, or the calculations we have for just how much heat is being dissipated. Only 1% of UVC light energy coming out and 3% heat energy from the LED, 45% coming down, 51% going out. The heat transfer mechanisms, for those of you who are familiar with such things, the heat radiation, natural convection, air movements, all help with this heat dissipation, which we think, again, is the mechanism for the low temperature. In our system, the LEDs are replaceable, so in addition to the lifetime that we would hope to get, extra lifetimes, we can also replace them. We imagine putting them in an array, so we have a uniform light emission with a sensor, and distributed light we see as the way to go for effective disinfection. This is a very rough calculation for what we might expect in what we would achieve, log 190% disinfection. This would require 36 LEDs. We could put them in an array, and we would, over 2.4 hours, achieve a 90%. So very rough idea, a rough calculation, but to give it an idea. In the future, we want to do more measurements using even higher currents and test the lifetime with more accuracy. We expect a 10 milliwatt output based on the new product by Selena that was just announced, called the Quad High Power. So in summary, high far UVC 235 nanometer power output was achieved in our fixture while staying well below the junction temperature, maximum temperature. And this proves that a fixture can play a very important role in the LED performance. So moving ahead, other LEDs might become available on the market. Those could be enhanced by a fixture that dissipates the heat. So thank you very much. This is our team, myself, and the founder, and Dr. Mark Lerville, Dr. Sven Pugson in Copenhagen.